Hi all. Today we're going to focus on reviewing some properties of logarithms that you've used before. We'll help you review these three properties that are going to allow us to simplify and to evaluate logarithmic expressions. The first of those three is called the product rule, and that simply states that the log base b of mn, or m times n, is equal to the log base b of m plus the log base b of n. And I would remind you that we said all along that the logarithm is an exponent, and you'll remember that when you are multiplying exponents of like bases, which we are right here, you add the exponents. Okay, that plays out right in this logarithmic rule, the same thing that we knew for exponents. So that's kind of cool that there are those connections. What I'd like to have you do is use that a few times. That is, we want you to expand log base 4 of 7 times 5, which is a product. So according to that rule, that log base 7 times 5 is the same thing as the log base 4 of 7 plus the log base 4 of 5. What started out as multiplication breaks out or expands into addition. So now we're looking at a common log. See, no bases there, so this is base 10, but the log of 11x, or 100x. This is a product, so the product rule applies, and we would break this one out this way. Log base 10 of 100 plus the log base 10 of x. The deal is, we know log base 10 of 100, the property or the power that you raise 10 to get 100 is 2. So we can simplify this one further by saying 2 plus the log of x. Again, where that 2 came from, that's 10 to the second power, and the exponent is the logarithm. So yeah, we'll just draw the arrow. Right? The exponent is the logarithm. The log base 10 of 100 is 2. Let's try this one. In fact, you should try this one on your by yourselves. This one is a natural logarithm, and 12 is a product. There are several ways that you could write this, okay? Because there are several different factorizations of 12. One possibility would be the natural log of 4 plus the natural log of 3. We should be able to do the natural log of 6 plus the natural log of 2. And just to prove to you that that is a possibility, I'm going to call my calculator up here again. Okay, there's our natural log of 12. And if the work that we did over here is correct, we should be able to ask our calculator to take the natural log of 4 plus the natural log of 3, and it should evaluate to that same 2.48. I sure hope it does. Oh yeah, there it is. Now again, 12 factors in several different ways, so we should be able to ask it for the natural log of 6 plus the natural log of 2, since 6 times 2 is also 12. Cha-ching! There it is. All right. So now we've looked at the product rule to expand things that were written in multiplied form, if you will. We want to go the opposite way here. We want to condense the log base 4 of 2 plus the log base 4 of 32. So according to what we said, this is broken out, at least that's the way I say it, it expanded as an addition. Then we should be able to condense it or shrink it into a product. So that would be the log base 4 of 2 times 32, which is 64. And folks, that can be simplified because 64 is a power of 4. In fact, what is the exponent that we would have to raise 4 to get 64? Well, 4 to the first is 4. 4 squared is 16. 4 to the third is the power that we need, so that becomes plain old 3. Let's try that again. Here we have the log, common logs, base 10 of 25 plus log base 10 of 4. So that's broken out, if you will, as an addition. We should be able to simplify it or shrink it into a multiplication. That would be the log of 25 times 4, which is 100. And this is a common log, so we're asking for the power of 10 that you need to get 10 raised to 100. So this one would simplify to 2. So we're learning some tricks to help us simplify and evaluate logarithms. Okay, that product rule is a handy tool. All right, our next simplification rule is the quotient rule. And you just looked at the product rule, which said that the natural log of a product breaks out as to the sum of the natural logs of factors. The quotient rule is like that. It says if we have the log base b of some quotient, some fraction, m over n, that has the same value as the log base b of the numerator minus log base b of the denominator. So log base b of m minus log base b of n. We're expanding here. So as we look at this one, we do have a quotient, so we should expand this way. The log base 8 of, and then the top one goes first, log base 8 of 23 over the log base 8 of x, whatever that might happen to be. The next one looks a little bit more frightening, but it isn't really. It's still a quotient. It would break out into the natural log of, and I'm going to write this in exponential notation, and that would be 5/3, e to the 5/3, right, the ratio, minus the natural log of 11. Some of you might be thinking, Mrs. Brownfield, I think you can simplify that, but I'm going to say we're not quite ready for that yet. We will be in just a minute though. The log base, or the log, common log of 10, well, we're talking about the quotient rule, so we'd be looking for things that divide to make 10. Things like 20 divided by 2, or 5 divided by 1/2. This should break out then. We start as a quotient. We should be able to break out as a subtraction. So the log of 20 minus the log of 2 is one way to simplify that. There are certainly many others, but I chose this one, the log of 5 minus the log of 1/2. And I'm going to just ask you to take a look at my calculator screen, and you'll see, sure enough, all of those. The log of 10 is 1, since the power you raise 10 to get 10 is 1. When I did log 20 minus log 2, I also got 1, and log 5 minus log 1/2 gave me a value of 1. So that's the expansion with the quotient rule. Here's the condense part, and condense just means you're shrinking. So instead of showing the difference, we're going to show a fraction here. That one on the left would be log of, and it's 4x minus 3 over x. Right? It was in its expanded form of subtraction. It condenses to a division. You try this one. Yeah, just like the other, we showed a subtraction, we shrink or condense to a division. The next of our simplifying rules is the power rule, and some of you will remember this. If we have the log base b of some number raised to a power, the power rule. The rule says that the exponent can actually come out in front and be the multiplier. So this one would simplify to n times the log base b of m. Okay, power rule. If you think about that for just a hot second, we could have done a little bit more simplifying up here because we have a number raised to a power. So if we were going to finish out this problem, that 5/3 would come out to the front, and we would be looking at 5/3 times the natural log of e minus the natural log of 11. And some of you are going to be saying, but wait, there's more. The natural log of e is just 1 because the power that you raise e to get e is 1. So really, that whole ugly, nasty thing simplifies to this: 5/3 minus the natural log of 11. Okay? We used the power rule there. We could have, we just didn't have it. So let's use it here. We have the log base 6 of 3 to the 9th power. Power rule says that 9 can come out front, and it will multiply the log base 6 of 3. The next one, well, it's the natural log of the cube root of x. So it might just help us if we remember that the cube root of x is really x to the 1/3 power. And so we can bring that exponent out to the front. 1/3 times the natural log of x is the way that one simplifies with the power rule. Here's another. The exponent 2 comes out to the front, and it would be 2 times the log of x plus 4. Very good. That's as far as we can go on that one. Let's turn the page because I know there's a quick warning for you here. It has to do with that problem that we looked at just the last example. And we just want to make sure that you realize log base b of some two numbers added together is not the same thing as log base b of m plus log base b of n. Those are not the same. Here we are totally broken out, both logs at the same base added together. That's not what this says, so we have to really be careful when we're simplifying something like this. We're going to mix up a few of these together now, and we're going to ask you to do your best here. We want to write each of these as a single logarithm. The base on both of these is e, since we have natural logs, and let's see, I believe we could do the reverse of the power rule and bring that up front, or out to the back, I guess. But do we really need to do that? Yeah, natural log of x squared plus the natural log of x plus 5. Now we do, folks, we're in this situation. We've got the logs of the same bases of things added together. So we should be able to join those or condense those into a, let's see, it's broken out as addition, so it should be a multiplication. It should be the natural log of, and it would be x squared times x plus 5. Or we could simplify further and say it's the natural log of x to the 3rd plus 5x squared. Moving on. Here we have something that's broken out as a subtraction. So when we finish with this, we should have a division. We can do the same thing that we did in the previous problem, that is the reverse of the power rule here, and say that this is log of the quantity x minus 3 squared minus the log of x. And since we do have now a subtraction of two like-based logarithms, we can condense that into a quotient. So this would look like the log of, and it will be x minus 3 squared over x. If you wanted, you could multiply out the top, but it won't allow you to simplify since x is not a factor of x minus 3 squared. All right, here's one for you to try. It's got lots of good stuff going on here. Two subtractions. I wonder how that's going to play out. Well, I do know that when you're simplifying, you approach things from left to right the way that they come. So let's see if we can break this into smaller bits that will be easier for us to work with. Log base b of x, and it's going to be raised to the 1/4 power. Do you see why? Because that's going to move back here. So I'm going to write that this way. Log base b of x to the 1/4 power minus log base b, see, I'm going to apply that power rule in reverse, of 5 squared. Well, that's just 25. Minus, wow, look at all of this, log base b of y to the 10th. All right, now moving from left to right, we should be able to say that we have, I'm going to come up here so that I have the extra room. log base b of, and it will be x to the 1/4 over 25 minus the log base b of y to the 10th. And this should also, since it's a subtraction in its expanded form, since it's a subtraction in its expanded form, should condense to a fraction. So we should be able to say log base b of x to the 1/4. And you'll remember in class we discussed what happens when you divide a fraction by another number. That 25 stays on the bottom, but the y to the 10th will be there as well, and all of that in parentheses. Yeah, that was a little bit more complicated. However, certainly within our ability to do, we can follow the rules. We're good at following rules. I think we have one more little thing to talk about today in our properties of exponents, and oh yeah, this is a biggie, folks. The change of base property says that the log base b of m is equal to, and okay, this is going to look funny, but you pick a base, log base c of m, the big thing, divided by the log base c of the base that you were in. Folks, this is going to be handy for us because you see where it allows you to choose any base. It will be a good idea to let c equal 10 because our calculator knows base 10 logarithms, or we could let our c equal e since our calculator knows the natural logs as well. This is going to allow us to evaluate any logarithm, even if it's some funky base that we're not sure what to do with. This is a powerful, powerful tool, especially when we're solving logarithmic equations. So let's see how that goes here. The log base 7 of 2,506. According to the change of base theorem, or property, if I choose my base to be 10, then I'd be working with common logs, and it would be take the common log of the top, or the big number, 2,506, I shouldn't say the big number, this guy, and divide him by the log of 7. Now, I don't know what those numbers are, but my calculator does. So I'm going to come over here, and I'm going to think, okay, I'm doing common logs, log of 2506 divided by the log of 7. And according to the calculator, that is about 4.0, right around 4. Okay. If you happen to have the Casio calculators, they do work in any base. So you could set this up on your Casio calculator to do it without the change of base, but it's a good thing for us to remember that the change of base formula works. And as far as I know, there's no way to do that on the TI-84s unless they've been improved since I bought my last one. Here's another one to try with that change of base theorem. And again, it's up to you what you choose as your new base. So let's work this one with natural logs. So e would be the base. We don't normally write that, but it'd be the natural log of 140 divided by the natural log of 5. And according again to our calculator, which we trust, the natural log of 140 divided by the natural log of 5 is equal to about 3.1. Okay. That change of base formula, it is so important for us to remember that. We will use it a lot, especially as we start solving logarithmic equations, which is going to happen very soon for us. Okay, that's the end of today's lesson. I thank you for participating. I'm going to ask you now to keep on, go back there and try that U-Try on the website. We want to get that turned in before school. That's when it's due. Have a good night.